Let's study this example of symmetries of a square some more. We listed 8 symmetries of a square, 8 transformations that you can do to the plane that takes a square to itself. You have 4 reflections across the x-axis, across the y-axis, across the 2 diagonals. They're called f1, f2, f3, f4. And then you have 4 rotations, you might say. Rotation, anti-clockwise rotation by 90 degree, 180 degree, 270 degree, or 360 degree. The first 3 are called R1, R2, R3. And the 360 degree rotation of the plane is same as not the identity transformation of the plane. So that's customarily called E for identity. These 4. And what we sort of indicated is that this set, which we call D4, E, R1, R2, R3, F1, F2, F3, F4, has this operation on it, a binary operation, where you feed in 2 of these ordered pair of these transformations, and it spits out again one of these transformations. How does this work? You just apply 2 of these transformations back to back, and the net result of the 2 transformations applied back to back is again one of these 8. We checked that for one example, applying F1 and then applying F2, applying the flip across the x-axis and then the flip across this diagonal amounts to a 90 degree anti-clockwise rotation. So we say that by writing applying F1 then applying F2 is R1. So F2 times F1 is R1. And you think of this composition as sort of a multiplication on this set, D4. So if you give me 2 of these things, 2 of these 8 things, I can multiply them and again get one of these. Multiplying here means applying them back to back. But you have to understand that the order in which I'm applying this, when I write F2 dot F1, it means first apply F1, then apply F2. Okay, that's what it means. Because these, we are thinking of them as functions, and when you apply a function, you write the argument, the thing that you apply the function to, on the right. So F2 circle F1 xy means F2 of F1 of xy. And that happens to be R1 of xy. And that is abbreviated by this equation. And similarly, one could work out what happens when you apply any 2 of these back to back. And you could sort of summarize that data in an 8 by 8 table that's called the multiplication table of this group, which tells you what this multiplication law is. By the way, this multiplication law or this composition law is called the group law of this group. So let's make some space here. And we'll make the multiplication table. So we have all the 8 transformations in front of us. So you write the 8 elements. This is called the multiplication table of D4, sometimes also called Cayley table, in honor of Cayley, who did a lot of foundational thing in group theory. Here are the 8 things. Here are the 8 elements of the group again. Oops, there's no R4. So in a typical spot in this table, like say this one, I'm going to write F2, F1, this thing and then that thing. And what is F2, F1? That's the thing that we calculated. It happens to be R1. So here we put R1. Similarly here, this entry, what goes in that entry is what happens when you apply F1 and then F2. And if you apply F1 and then F2, oops, I'm sorry. What goes here is F1, F2. Which means what happens when you apply F2 and then F1. We apply from the right? F2 and then F1. If you do that computation, you'll see that this amounts to anti-clockwise 270-degree rotation, or clockwise 90-degree rotation, which is the thing that we call R3. Okay. So you already see that the order in which you do these operations sometimes matters. Let's just record this is F2 times F1, which means first F1, then F2. I'm just repeating this thing because it's sort of awkward reading from the right. Okay, let's fill in some other entries. The first row is very easy. What should go here? What should go here is R2 times E, which means first apply E, then apply R2. Applying E means doing nothing, and then you apply R2. So that just gives you R2. So this row is basically just, and this similarly here, because this is same as saying what goes here is F1E, which means first apply E and then apply F1. But if you first apply E, that does nothing, and then you apply F1, that's the same as just applying F1. So this is just F1, F2, 3, F4. And that tells you that this identity element is a special element which has a property that when you multiply it with any element of the group, you get the element back either way. That's going to be one of the group axioms for all A. Okay. Then when you apply R1 with R1, you get 90-degree rotation, then 90-degree rotation again. So that's 180-degree rotation, R2. 90-degree, here goes R1, R2, meaning 180-degree rotation, then 90-degree rotation. That's same as 270-degree rotation. So that's R3. And this one is 270, then 90. So it's identity. R2 and then R1 is also R3. So in this case, you see R1, R2 is same as R2, R1. So they commute. So AB equals BA sometimes holds, sometimes doesn't in this group. Then R2 and R2 is two 180-degree rotations, that is 360-degree rotation, which is identity. This one is 270, 180 amounts to 90. Then this is E again. R2, R3 is R1, R3 is R2. Okay. And maybe you can fill in the other entries. These are easy to fill, for example, the diagonal. Here goes F1 times F1. So you apply the flip twice. Reflect across the x-axis, again reflect across the x-axis. You do it twice and everything comes back to itself. So you can see this transformation is really taking x, y. It negates the y-axis. Right, that's what F1 does. If you apply it again, then you go negate it again, but then it's back to xy. So this is just the identity transformation. So doing a reflection twice just brings it back to identity. Okay. That shows you something, some other axiom. It tells you that for every element of the group, there is another element, such that when you multiply them in either order, you get the identity. See, every row contains identity, and every column contains identity. So for every element, there is another element, such that when you multiply them, you get the identity. Meaning each of these transformations can be undone by another transformation. So for each, there exists in the group, there exists another guy, B, in G, such that when you multiply them in either order, you get the identity. That's going to be another axiom of a group. It's called the inverse axiom. So this B sort of acts as an inverse operation of A. And then the other one is basically function theoretic, that it's some law that we already know for transformations, that A applied to B composed with C is same as A composed B composed with C. And this just comes from the fact that these are, in this example at least, the elements of the group are transformations. So they are some sort of functions. And when you compose and the group operation is really just composition of functions. So when you compose functions, composing two functions and then composing with another one on the left is same as composing the two left ones and then composing on the right with the third. This law we know. This is called the associativity law. So a group is going to be a set together with sort of a multiplication law which satisfies these three axioms. We'll write it down next time and do some more examples. And you can fill in the rest of this table rather easily.